Hello everyone. On behalf of the Victorian team at the Institute of Architects, I'd like to offer you a warm welcome to today's lean-in, Demolition is Dead, Why the Best Buildings May Already Exist. This session will provide an overview of the compelling benefits of seeking to reuse our existing building stock over new construction, including why embodied carbon matters and critical factors to consider in making the economic and environmental case for adaptive reuse. My name is Stephanie Bullock and I'm from Kozloff Architecture and sit on the Institute's Victorian Chapter Council, and it's my honour to be your host and moderator for today's lean-in session. We're joining from across the country today and we acknowledge with deep respect the traditional owners of this land. We acknowledge that it is a privilege to stand on country and walk in the footsteps of those before us, and we pay our respects to elders past, present and emerging. This lead-in session is being recorded, so if you miss anything today or have to leave early, we'll be publishing this recording on the Institute's YouTube channel in the next couple of days, and we'll share that link with you in our upcoming email communications. This lead-in session also enables you to ask questions of our panellists, so if you have a question or comment, please use the Q&A box at the bottom of the screen to add yours in, and we'll go through these later in the session. Our presenter today is John Bahoric from OVGA. John has extensive experience working across complex multi-sectoral and multidisciplinary environments, driven by sustainability and end-user amenity outcomes. He provides leadership across projects and the broader multidisciplinary capability at OVGA across a range of sectors, including health, education, defence, public realm, galleries, museums, sport, transport, commercial and retail. He also provides regular input into the OVGA Design Review Panel. John is driven by design-led sustainability and supports the provision of amenity and future-proofing to new builds whilst minimising carbon footprints. I'll hand over to you now, John.
Thanks, Steph, and thanks for the opportunity. So today I'm not controlling my slides, they're being controlled across the other side. So I will just click on the next slide or next part. Yep. Sorry, is someone stepping through the slides? That's it. Okay. This might be painful. Okay, so today I wanted to go through, so the title of the talk today is Embodied Carbon Adaptive Reuse. I wanted to go through very briefly our climate crisis. I wanted to go through EPDs, Environmental Product Disclosure Statements, and how they relate to life cycle analyses. I'll go through some building topologies, including Ballarat Biennale building, which is still underway, the RMIT New Academic Street, and together with also looking at decisions around adaptive reuse and what your decisions mean and what it means to be cognizant of carbon footprint as we move forward. So next slide. Next slide. So just to paint the picture, I'm sure people are aware of just how dire our situation is, but our climate has changed and continues to change, and it gets dramatic every year. So every year I actually update this slide. And over the past 12 months, we've had record flooding in Western Australia and Queensland of the order of 1.5 to 2 metres, which is extraordinary. We've had 60,000 deaths in Europe due to record temperatures across Europe. As I said, due to an unprecedented heat wave. And in Canada, we've had bushfires raging through Canada that's destroyed up to 5% of their entire forests, which is an equivalent landmass of about the size of England. And the severe storms that are occurring on a regular basis is leaving insurance companies with issues around how to actually reinsure their business and how to provide appropriate levels of cover moving forward in our very difficult environments. And if we go on to the next slide. And this is being driven by growth in emissions effectively since the beginning of industrialisation. And emissions are mainly coming from coal, oil and gas, together with deforestation. So you can see the figures at the top. Coal's predominantly the main source of emissions, 15 gigatons a year, together with oil, about 12. And all up, this is creating about 42 gigatons of emissions a year, which is an extraordinary amount, and unfortunately, it is still on the increase. So if we could just click through a couple of points here on our slides. The Paris Agreement asks us to hold the increase in the global average temperature to well below 2, and to pursue efforts to limit the temperature increase to about 1.5 degrees. And unfortunately, we've actually already reached 1.5 degrees, and to limit greenhouse gas, to limit global warming to 1.5 degrees, we would have had to have reached our peak before 2025 at the latest, and decline to about 43% by 2030. And unfortunately, 1.5 degrees is already locked in. So could you just click through the slides, please? And if we reach 2.5 degrees warming, that'll be a temperature the Earth has not sustained for at least 3 million years. And under our current policies, we're set for an increase of about 3.2 degree rise. And not meeting these current policies, we'll get to about 4.8 to 5 degrees. So we're actually heading for quite a disaster, unfortunately. We're about 740 gigatons away from approaching a 2-degree temperature rise, and that's about 15 years away. So unfortunately, we'll be heading for high temperature rises within our lifetime, and the action and the impetus to do so is now. So could you just click through the slides, or click through those points, please? Yep, just keep on going. That's it. Next slide. And the reason why we're here talking about this is because if you look at global CO2 emissions, buildings make up about 39% of emissions, together with transportation about 23%. So in the building sector, we're responsible for about 39% of emissions, which is about a quarter of that is attributable to embodied carbon, about 11%. So the decisions that we make as designers are very critical in our ability to influence and reduce both operational and in particular, moving forward as we decarbonise the grid, embodied carbon. Next slide. And there's a couple of other points that tie together neatly, which we should be cognizant of. So resources will become difficult to extract. It's predicted that we'll have a resource shortage as our building stock effectively will double in the next 40 years, and the cost of resources will concurrently increase with material demand, which will outstrip supply. And as we decarbonise the grid, so as solar panels and wind take over from coal, it'll be increasingly embodied carbon that will become most heavily scrutinised. And next click. And in terms of what we're doing as a government, because compliance is a lever, so the compliance landscape is changing, and in Australia, planning laws are being recut that will require developers to measure their carbon footprint for brownfield and greenfield sites prior to or conditional upon getting their planning approval. And it's likely that will be implemented nationally by the EPA, and that's currently being undertaken by Tanya Plibersek with help from Graham Samuel in Victoria. And that will then force us or compel us to actually report on carbon to get out both our planning approvals and building approvals and ongoing reporting in the same way that we report on tax at the end of each financial year. One more click, and if we compare that to France, for example, so France have passed a new law that compels developers or builders to effectively have at least 50% of their materiality to be regenerative, which basically points to timber as being a major material component for use through moving forward through French building stock. So there are definitely compliance requirements that are now being increasingly implemented across the world, which recognise the dire situation that we're in. Next slide. And when we do talk about emissions, I just thought it would be useful to talk about some definitions first. So the common language is Scope 1, Scope 2, Scope 3. So Scope 1 refers to direct emissions from on-site fuel combustion, gas turbines, machinery, vehicles. Scope 2 refers effectively to electricity, heat, or steam that you buy from the grid. So when we talk about removing Scope 2 emissions, we're effectively talking about decarbonising the grid and shutting down coal-fired power stations and replacing those with wind or solar or other green sources of power. And Scope 3 refers to, and this is what the planning laws will target. Scope 3 refers to products that you buy. It refers to your business travel, your when you're on aircraft or aeroplane travel. It refers also to the materials that come out of the ground that are processed, refined, and purchased, including fuel. And that forms essentially the embodied carbon that goes into your building. So Scope 3 is essentially the next sort of big component that's being targeted. Next slide. Now I'll talk a little bit about life cycle analyses and also environmental product disclosure statements that sort of take us towards how we are measuring embodied carbon and how that can inform better material use. So next slide. Next slide. So I'm sure a lot of you have seen something like this before. It's a common diagram. It shows you essentially a life cycle analysis, and it's the basis for carbon accounting. And it essentially measures environmental aspects and potential impacts throughout the process, throughout the life and the associated processes of a product, i.e. cradle to grave. Now, life cycle analysis, they're referenced in ISO 1400 series, so they do come from and refer to a codified approach. They're not necessarily mandated though, but there is an international approach to doing this, which I'm pretty soon, I'm sure, will become mandated. And as designers, and if you look at the chart carefully, as designers, we can influence upfront A1 to A5 emissions, which is essentially the materials that come out of the ground or a forest that are turned into product. We can influence B1 to B5, which is during building use. And we can also influence C1 to C4, which is basically the end of life process. So as designers, we do have a large say and a leadership role in making sure that our choices around how we design and what we design can be justified in terms of carbon footprint. Next slide, please. Now, this slide is a snippet of an environmental product disclosure statement. And environmental product disclosure statements are very important because they give us a research-based measure of carbon content of materials and products. And they essentially feed directly into a life cycle analysis. And they're becoming a standard and accepted way of measuring carbon. The issue with life cycle analysis is that if you have 5 different people measuring a material in 5 different ways, you get 5 different answers. And your life cycle analysis then can become difficult to interpret. So with accepted ways of measuring carbon and accepted ways of publishing information and reading it, it does give us a standard sort of unified way of moving forward. So for example, for timber here, and this was produced by Wood Solutions, when it comes out of a forest, it's basically almost entirely carbon. You've got 1,017 kilograms of CO2 per cubic meter. And then through the harvesting process, you actually lose 230 because of the machinery that's required to cut or to retrieve the timber from the forest. You've got resin glues, you've got manufacturing processes and packaging. And by the time it's available for purchase and it becomes part of your building, you still end up being carbon negative. It's about 612 kilograms of CO2 per cubic meter. Which makes it a very favourable material, but every time you do something to it, you're slowly sort of eating away at that carbon bank. And on the right-hand side, if the material is burnt or reused or recycled, and the life cycle analysis process doesn't allow you to use timber carbon credits for more than one project. So in other words, if you're banking timber on one project, you can't take that timber out of the project and use it for another one and then count the points twice. It only allows you to count the points once. So on the second project, it actually assumes, and subsequent, it assumes that carbon is released into the atmosphere, and that's why it's a plus 1,000 for reuse, recycling, and energy recovery. The alternative, of course, is landfill, and there are two ways of calculating that, but essentially landfill, sending timber to landfill means that it starts to react and form methane, and which is actually worse for the environment, and that's released back into the atmosphere. Now, on the next slide, what I'd like to do is progressively go through different materials and start to reveal the carbon footprint of each material. And I've focused on 4 primary materials, so concrete, steel, aluminium, timber. And for the first material, which we've just talked about, please click. For the first material, we've got, so all I've done there is tabled what I've talked about in my previous slide. So we've got for components A1 to A3 in our life cycle analysis, we've got minus 610 kilograms of CO2 stored in timber per cubic meter. And on the bottom, if we flip that around, it adds up to about 941 kilograms of CO2 per ton. So effectively, timber is entirely carbon. Now let's compare that to concrete. Next click, please. So concrete releases 410, and this is a standard mix, 32 MPa. It's referred to as the Australian National Life Cycle Inventory Mix. So it's a benchmark. That releases 410 kilograms of CO2 per cubic meter, which is almost exclusively and entirely in the production of cement. And when we produce cement, it gets heated, constituent particles get heated to about 1,500 degrees, and that's where all the energy is released in its production. And then if we flip that around at the bottom, weight per ton, it's about 171 kilograms of CO2 per ton, which isn't too bad, except we use concrete on foundations, we use it on floors, columns, beams. It tends to add up because it's omnipresent. So let's compare that to steel now. So steel is horrifically high. If you look at the bottom and compare it to concrete, so for every ton of steel we produce, we release 3.2 tons of CO2. And that's because steel has to be heated in a blast furnace to about 4,000 to 4,500 degrees centigrade. And that's where all the energy is consumed. And even recycled steel has to go back into an arc furnace. And that's also up at about 3,500 to 4,000 degrees. The difference between recycled steel and steel that comes out of the ground is essentially that you're removing the mining processes, but it still is very carbon intensive. So using recycled steel isn't necessarily saving the world, unfortunately. And last but not least, now this material is not structural, it's effectively architectural, it's used in finishes, but it's 3 times more flexible than steel. So you'd never have aluminium columns or beams, but it's malleable and it's incredibly energy intensive because of the production process. So 16.7 tons of CO2 is produced for each ton of aluminium. So it's good to try and minimize that where you can and to be cognizant of how bad it is. Next slide, please. And I want to compare that now to some other sort of finished materials that you might use, finishes. So next click. So for example, glass is about 1.1 tons of CO2 is released per ton of glass produced, and then we can compare that to plasterboard, which is about 169 kilograms of CO2 per ton. It's not too bad, but again, these materials tend to be used more often as fit out and they become omnipresent. We compare that to terrazzo tiles, which figures disappeared. From memory, terrazzo tiles is 80 kilograms of CO2 per square meter. And the last one is vinyl carpets, which is about 11 kilograms per square meter. So obviously, the figures get smaller as the materiality and end use becomes sort of less structural, so to speak. But it's more about being cognizant of how often you're using it and how often the cycle of refurbishment and fit out occurs. So next slide. So essentially, in learning about environmental product disclosure statements and the basics of materials, we start to now look at how embodied carbon is actually distributed through a building. And the top right-hand image, which I borrowed from the GBCA, if you look at on the right-hand side, superstructure plus substructure, that's your concrete, steel, and whatever else. That's about 55% of embodied carbon, which is quite high. The transportation to get all your products to site is about 10%. And then on the left-hand side, you've got 20% effectively services and fit-outs, MECLA and finishes and fit-out, and then 15% for your facades. So an appropriate way of focusing on carbon early on is to get a good structural engineer to make sure that you're refining your design, because a good engineer would be doing that anyway, and also being cognizant of the materials that you use and ensuring that you've got the right durability and the right sort of fitness for purpose of design that achieves what you're trying to set out to do with your client, as well as being able to continue to use the building well into the future without having to reconfigure it in complex ways moving forward. So if you look at as well on the bottom, I've got typical floor plate structure, kilogram of CO2 per square meter. So at the top, I've got residential PT slabs, generally 100 to 120 thick, and literally that's 100 to 120 kilograms of CO2 per square meter. And on the right-hand side is the total CO2 per square meter of floor for essentially a building. So on the left-hand side, it's the structure only, on the floor structure, and on the right-hand side, it's the total amount. And as we go down, the design loads increase. So for education buildings, it's typically 150 to 175. For public buildings, it's similar figures, 130 to 160. And for health and laboratories, 150 to 175. But you need also, for buildings that are sensitive to vibration, you need to make sure that you have adequate stiffness and materiality to design for that. Next, I guess what that slide shows as well is the fact that there are targets, meaningful targets, and it's very easy to exceed those by being a bit nonchalant. But these targets are very achievable, and we should be doing that as a baseline, I think. So a figure of around 150 is a good figure for the bottom three topologies. Next slide. So now I just wanted to talk a bit about sort of experiences with existing buildings. Next slide. But before I do that, a good starting point when you adaptively reuse is to try and understand what you've got, what's been there before, and in particular what your floor plates are designed for, because that allows you then from the onset to understand where your realistic aspiration lies. So, for example, this table here simply describes the design live loads for different types of buildings, and the most heavily loaded existing types of buildings are industrial type buildings or workshops. And then you go down to retail libraries, which are about 400 kilograms of live load per square meter. Laboratories down to 300, restaurants and cafes 200, and then residential apartments or houses or buildings about 150 kg per square meter. Intuitively, you can convert a retail building or a library into a restaurant, or you can convert a restaurant into resi, but it becomes very difficult and very expensive and problematic to convert a residential building into an education building, because you're effectively asking for the live load, the floor live load, to be doubled, and that can't be economical when it comes to adaptive reuse. It's also important to note that the top sort of 3-4 topologies, generally speaking, they're open plan, they're contiguous, And with resi, quite often it's defined by structural walls, and it becomes difficult then to remove those or to create open plan, particularly for towers when you're wanting to have open plan workspaces, for example. So it's hard to go from a residential tower to an office building because of the design loads and the way the building's been configured. Next slide. Next slide. It's also, sorry, one before that. It's also good to understand when buildings were built and the technology of the day and what that means in terms of how the building performs and what you need to do to upgrade for today. So this is a very, very quick summary. I've broken it down into sort of 4 types of eras, if you like, but there's a lot more than that going back to the 1850s. So when we're dealing with sort of gold rush buildings, architecturally significant, they're heavy masonry structures, they have closely spaced walls, they have bluestone foundations, heavy materials, they're very brittle, which means they don't perform very well under earthquake loads. They'll often have timber floors or wrought iron floors. They generally will require dispensation to satisfy current day earthquake loads. And you are relying on the vertical structure to both to provide vertical stability and also horizontal stability under wind and earthquake. So it becomes an interesting process of figuring out which walls you can and can't remove and the consequence that has to the overall stability of the building. The second type of structures down below, we're now going into a sort of a more industrial era. These are welded steel frames, which were prolific through North America, Europe, and Australia. So the welded steel frames get their stability from the stiffness of their connections. Good examples of these in Melbourne are RMIT, buildings 8, 10, 12, and Orica House. There's a whole lot of others in Melbourne. And effectively, as long as you maintain enough welded connections between the beams, that gives you your horizontal stability, and then you can start to punch holes between those beams to create sort of vertical thoroughfares if you're trying to connect spaces together vertically and adaptively reuse those. And as long as you preserve enough of the welded steel frame, you can make substantial embellishments. Next slide. So then we move into an era of sort of a more modern era where we've got composite beams. So this is 101 and 120 columns, for example. We've got a central core that provides stability to the building, and then the floors lean on the core. In this case, the floors are made up of steel beams supporting Bondex slabs. And provided you don't interfere with the steel beams, you can punch holes through your Bondex slabs, or you can start to reconfigure your floors around removing steel beams if that's what you want to do. But it does give you some flexibility there because all the reinforcement is passive. The issues that become prevalent are when we start to look at the last example, which is tall residential buildings, or buildings essentially that use post-tension floors. So they are by far the cheapest to build. So post-tension slabs are king in Melbourne and Australia because of their cost. But when you try and cut those floors, particularly non-grouted PT strands, it becomes dangerous. The strands recoil. And because there are far fewer strands per square metre, when you start to cut 1 or 2 strands, you significantly reduce the strength of the slab. So you need to be very careful about how you manipulate or change those slabs for post-tension floors. They're not very easy to adaptively reuse and reconfigure. Next, I wanted to go through very quickly the Ballarat International Photo Biennale building, some of the lessons learned there around what we saw. Next slide. So I'm just seeing a black screen. Next slide.
Just bear with us, everyone. We've been having some technical issues with the slides, so we're just restarting by the looks of it. Perhaps, John, while Elisa brings that up, did you want to give a bit of background on the project?
Yeah, I'll just keep on talking. So Ballarat Biennale buildings are 150-year-old building that was essentially a bank. It was essentially a location where gold from Ballarat was brought in and sold, exchanged for money. What that meant was that the building was very, very resilient. It was quite strong. The floors, there was a number of foundries in there, so places where gold was melted and then and ingots were created. That meant that we were dealing with floors that were quite robust. We're talking about 220 deep, 240 deep joist, 60 wide. That gave us a floor capacity of about 5 kPa, which is incredibly good. And for some of the existing long span structures, next slide, please. For long span structures, we had wrought iron girders that were riveted that created sort of column-free spaces or wall-free spaces. And it gave us something interesting to work with, I guess, in terms of a building that could be fairly readily adapted to a gallery. Of interest as well were the bluestone foundations. It was difficult to try and strengthen those to get it up to current earthquake code requirements, so we sought dispensation in that regard. Next slide. This shows essentially what we were dealing with in terms of the composition of the walls. So we've got effectively limestone mortar holding together sort of brickwork that was also then held by a 1 centimetre thick or thereabouts limestone render. So together, the whole assembly was quite strong, and it gave the building and the walls a lot of resilience. But the issue was, before we got there, some of the demolition crew were sort of up ahead of themselves. They started ripping out wiring, which then ripped out some of the mortar, which meant that the walls and were damaged, which then reduced sort of the performance of some of their conditions. So it's always good to figure out what you've got before you go in there to start to sort of change things a bit too quickly. But the important thing about these walls as well, and this materiality, was that you always need to use like-for-like materials, or materials that are compatible when you're strengthening. So you need to be cognizant of what you've got before you start to specify your new materials. Next slide. A common challenge is of the chimneys on older buildings, and these chimneys were, as I said, connected to the foundries that were used to melt the gold. They're tall limestone concrete structures, very, very lightly reinforced, and they'll probably be the first thing that comes down in an earthquake. So it's always a challenge to reinforce these from the inside and sometimes from the outside, noting that you need to meet heritage requirements where there's an overlay. But generally the balustrades and the chimneys are the first to go during an earthquake. The next project I wanted to go through very quickly is RMIT New Academic Street. And this was a truly great example of the best building is the one that's already built. I think it's a fantastic example of getting the most out of a challenging existing build and then augmenting that with an appropriate sort of scale and form of new build. The next slide. So in very quick summary, 32,000 square meters of new and refurbished space. A highlight for me were the new east-west laneways, and they also created, I guess, shopfront spaces. And most importantly, they linked Swanston Street effectively to Bowen Street. And they provided a fantastic level of sort of transparency through the building, so it made it a lot easier to navigate your way through all these spaces. And it was a very, very successful and sort of smart use of interesting interventions. Next slide. So these buildings were fully welded frames, a bit like what I discussed earlier. We had to break out a lot of the connections just to make sure that what we saw in some older drawings is what we had, and by and large it was there, which meant that all the holes that were punched through the slabs were done between the steel beams. So we had to maintain the connections between steel beams, because it's those connections to the floors that also not only provides vertical stability but also horizontal stability under sway action, under wind and earthquake, together with also figuring out how resilient the building was under earthquake loads, and seeking at the front end of the project a pathway with building surveys as to how to achieve resilience under earthquake loads, and also seeking dispensation where required. Next slide. I guess a key part of it was converting, the older version of those buildings which were inward looking, very limited to poor connectivity to Swanston Street, a bit confusing when you're inside, a bit dark. And then when you go to the next slide, and I do remember having a chat to Rob Adams, who walked past when he saw this, when I was with him one time, and he was quite pleasantly surprised and amazed at how the right interventions created such a big change to the ability of the building to become a lot more user-friendly, and how the puncture points and the balconies as well created opportunities not only for more floor space, but a way of bringing in more natural light into the building, and making the buildings and the way that all three buildings work together more interesting. And suffice to say that there's a lot more natural daylighting, ventilation improved, and far better outcomes around vertical and horizontal circulation. Next slide. So the next couple of slides demonstrate the benefits of I guess creating the right interventions between our existing steel beams, and in some cases preserving the concrete around them, in other cases removing the concrete. The beauty is that the concrete provides fire protection to the beams, which then helps, in terms of meeting BCA requirements. But essentially, it was a bit of a labour of love in just determining the combination of areas that could be punched through to create the best sort of architectural and I guess structural outcomes. Next slide. Sorry, next slide. Yeah. So one of the buildings I want to focus on very quickly, that was just a quick case study. This was the garden building, New Academic Street, and it sits adjacent an underground car park, but it demonstrates as well the effectiveness of using the right material for such projects. The material here was almost exclusively timber with steel that was fitted out around the facade. The timber came from Australian Sustainable Hardwoods in Gippsland. It was a stick frame building. You could see the bracing at the bottom, so express bracing. Bracing means it's easy to erect and disassemble. And this building took Lendlease it was constructed in very, very quick time. So next slide. And some of the benefits of timber, just very quickly, we know that it's sustainable as long as forests are regenerated. So forest management is key to making it sustainable. It's the only construction material that sequesters carbon. It does have a very important story to tell around biophilia and the resultant improvements to health and well-being to participants or to end users of the building. And it's very easy to use and to cut and to adjust on site. So it does contribute to speed in fabrication and prefabrication, which makes it cost effective. And it works very well with our digital sort of environments where you can send files off overseas and then you come back with a Meccano set full of pieces in a container that enables you to then put your building up. Next slide. In this case, the Vic Ash, which is a sort of a weaker hardwood, there was protection provided to the timber with a polyurethane coating. There were pedestals which were used to lift the timber off the ground in order to preserve it against water damage and infestation from termites. And the pieces were brought out as long sort of double span pieces that meant that minimized our connections on site. And we could do that because timber is very light. And you don't need, big sort of craneage requirements to lift it in place. It makes it more maneuverable on site and quicker to build. Next slide. And the floor system that came with it was essentially prefabricated concrete panels that was fitted to the timber beams. and then they were lifted off the back of a truck and joined and essentially plonked onto primary beams on site, and then they were plate connected, as you can see through the recesses, allowing for plates to keep all the pieces together. So it was acting as one big diaphragm. Next slide. And the benefits of timber around new build and adaptive reuse are immense. You get lighter foundations, you require lighter foundations, which means that when you are adding timber to existing build, you've got a better chance of getting more floors on there and for it to work with the residual capacity you've got. Lighter craneage, faster insulation, lower earthquake forces. I'll go into that on the next slide. It's cost-effective, time-effective, and your quality of finish is better. And timber does have the best strength-to-weight ratio of all materials. Steel can span longer. Concrete it has its purpose around floor plates and resilient sort of foundations, whatnot. But timber, there's a sweet spot for timber around mid-rise buildings between 2 and 8 stories, where it's incredibly economical and easy to use. Next slide. And this was a project we looked at a few years ago, 99 Queen Street, existing building. There's a structural model on the left. So we were limited by the amount of floors that we could put up as a result of gravity and earthquake loads. So putting earthquake loads compel you, when you do an analysis, to redistribute the loads so that you get more loads at the top and fewer loads at the bottom. It's almost like a pendulum effect. And on the left-hand side, we could only put on the left-hand sort of the blue triangle, we could only put on 3 additional concrete floors, beyond which the earthquake loads became very, very high. And on the right-hand side, when we use timber, and the participation of timber to earthquake loads is in yellow, because it's lighter, you got less mass moving. We ended up going with 6 floors and not 3. And we achieved lower loads and easier sort of pathways to compliance. So there's a compelling case for using timber to be able to get more floor space for adaptively reused buildings. Next slide. And some sort of tips around approaches to sort of when you are doing extensions or even I guess better ways of design. In our sort of carbon sensitive environment, it's always good to design for disassembly. That means creating sticks effectively, using simple bolted connections, and also trying to use cross bracing rather than moment frames, because cross bracing uses lighter connections, which are then easy to construct on site and easy to deconstruct. So all of these components can be reused somewhere else down the track. And I've got another slide that demonstrates that. There's also a compelling case to do more with less, to try and remove your layers between primary structure and facade, for example. Try and use the primary structure as your support to facade. The new Green Star does reward you for removing what they deem as unnecessary layers and using members for dual purposes to avoid secondary structure where possible. And that also helps you to sort of remove building clutter. And in terms of the case for adaptive reuse and also looking at the condition of your building, it's important to note that although the concrete might be degraded, and there might be a case for doing a lot of concrete cylinder tests to determine the strength, which then can tell you about the condition and any sort of rehabilitation work that you need to do. It's important to note that the steel doesn't typically degrade in the way concrete does, although rust is an issue. But the point being that if your concrete strength, for argument's sake, decreases by 50%, it doesn't mean that your floor plate decreases by 50%, because the steel is of the same strength. Concrete is important. It just means that your structure becomes increasingly more brittle. And as long as it complies with the codes, you can still use that concrete in those floors in a safe manner. But you just need the right engineering approach to get to that determination. And last but not least, concrete does have great thermal mass properties. We should use those. Why demolish something that's functional and may have some splendor about it, and does provide a cool place in summer. It does provide a cooler place in summer and does sort of store and release heat when the temperature is regulated inside. And it does allow you to then control your heating costs because of the regulation provided by that material in terms of its slow release or absorption of heat. Next slide. And just to demonstrate how timber is versatile and how a stick frame is versatile, which is the point of my previous slide. So this is the International House building in Sydney, and the columns on the left-hand side along the colonnade, which sit on top of those concrete pedestals, they came from a bridge that was 87 years old, built in 1935. And the columns were taken out of the disused, decommissioned bridge. They were joined together in clumps of 4, bolted together. The timber was obviously regraded. It was reviewed to ensure that it was still structurally okay, but it effectively has now made its way into another building for another 100+ years, I guess. Point being that with the right species and the right approach to design, there's no reason why these components can't continue to have a life through the circular economy and end up in different buildings through the course of the evolution of the built environment. Next slide. So last but not least, expectations for carbon reduction. So next slide. So what I've summarised here with some of the changes to the approach that Green Star are taking, and they are very pragmatic in what they've done. It's very much a design sort of led process now. And some of the outtakes of this, it's hard to capture all of it, but I thought it'd be useful just to point a few of these things out. So key outtakes are that they're expecting or demanding 100% renewable electricity in your buildings by 2026, which means that effectively removes all your scope 2 emissions. There's an expectation that by 2026, you will achieve 20% reduction in operational energy. Noting that these targets are we're moving incrementally towards these targets. So the expectation is that your design becomes better and the workforce delivering this becomes more skilled, and the expectation of sort of society and clients moves with it in order for us to achieve our Paris Agreement targets. So upfront carbon emissions, that's the materials that we choose, which we've gone through. There's an expectation that by 2030, we will be 40% better compared to what we're doing now. And scope 1 emissions, so that's basically on-site diesel or some of the gas-fired sort of plants. For example, Latrobe has one. There's an expectation there that will be eliminated. And there's also an expectation of offsetting emissions from demolition of existing buildings. So essentially, what Green Star does now is that where there's an existing building that's less than 30 years old, that is proposed to be fully or partially demolished. The expectation is that the embodied carbon calculation must be done for the demolished portion of the building to offset the emissions. So there's a keen onus, or there's an onus there if you use Green Star for your rating pathway. There's an expectation that you won't just demolish and start again, that you will try and reuse something that's less than 30 years old. And if it's between 30 and 50, there's a sort of a scale that makes it less onerous, but effectively there's an expectation that you will find savings in carbon that offset the unfortunate consequence of demolition, which does often lead to materials going to landfill. So 2 slides left. Next slide. What I wanted to show here were the choices that you have and the consequence of that around the carbon footprint compared to a new build. So we just might have to click through this. So if you're doing minor fit outs, the expectation is that your footprint's about 10% of a new building. If you're doing fit out, major fit out with services, that's approximately twice as onerous as doing minor fit outs. And if you then start to look at your facade, which adds another 15%, then you're up to about 35%. So a major bit of fit out with a new facade is about it's 65% better in terms of CO2 footprint compared to a new build. Next slide. So this is where it gets a bit complicated. So if we've got an extension and a refurb, what I've assumed there is that that's about 20% due to the refurb. 20 to 35%, depending on if you're redoing the facade. And then you also have to account for your new build. So there's a percent. So depending on the scale of your new build, so your new build will include mech and elec, it'll include facades, it'll include your superstructure and substructure, and the construction as well. And those last percentage figures are scaled up and down depending on the size of your new build. And the one that that you need to be most wary of is the complete demolition and new build. So effectively, your old structure is written off, which incurs an extraordinarily high carbon footprint, and then your new structure will then create the double whammy effect, where you're removing old structure and then getting new materials mined out of the ground for your new structure, which unfortunately is a pathway to much of the built environment today, which needs to change. So next click. And yeah, so essentially they're the sort of 5 broader decisions that you've got to make when it comes to looking at your existing building. And it's good to be cognizant of the sort of the effect that your decisions are having on how materials are being used or not used, and where they end up, whether it be landfill or otherwise. And that's my last slide, and that brings my presentation to an end. Sorry about some of the technical issues. It wasn't the way we planned it, but I hope the information got through there, and very happy to answer questions. And I hope there was something in there for everyone in terms of just inspiring you to read a bit further, to become a bit more educated and a bit more sort of capable of taking on your next project with a carbon-friendly outcome in mind. Happy to answer questions.
Thank you so much, John. That was great. So we've had a question come through. I'm not sure if you can see it. If everybody clicks on the Q&A at the bottom, and it's particularly relevant, I guess, given those last few slides that you've shown. But not all clients, I guess, are willing to consider the lost carbon footprint, and it may not be a Green Star rated project.
Yep.
What advice do you have for architects in terms of advocating for that, or educating clients about the importance of that?
No, that's a good point. And to be quite blunt, we're behind culturally in this sort of realm of thinking. We are behind Europe and much of the world. The long and short of it is that at the start of 2025, companies will have to start reporting on scope 1, scope 2, scope 3 emissions, and the first lot of companies that do that are the larger ones that have over $500 million in turnover, and slowly but surely that requirement will roll out to all business, and that requirement then will start to capture the work that we all do. So they're going to start to look at scope 3 emissions, which is embodied carbon. So that's the stick that's coming, and the legislation's written, and it's real, and it'll be subject to tweaks, no doubt. But it was supposed to come into effect July the 1st this year, but it was pushed back 6 months. And I'm sorry, I should have had slides on this, but the question is, where do you stop? Because there's so much content that you can bring to this discussion. But effectively, in the way that I'm answering your question, those consultants who are capable of running the narrative and running the solutions around low carbon will be the ones that will prevail next year onwards in providing a level of service that is relevant to protecting the business interests of companies like GPT or ISPT, those that have infrastructure or buildings at the core of their sort of net worth. In order for those buildings to also maintain their value, they also need to demonstrate their ability to tenants that they do perform and do provide a basis for favourable reporting to the carbon bottom line, so to speak. So I guess my answer is, if we're having issues with motivation, there are compliance, there's laws that are changing that will change people's motivation, and when that happens, those with the know-how, consultants, leaders in this field, will find it far easier to get work than those that think that business as usual is the best way forward, because it's not going to be like that forever, and we're probably heading to a cliff. But it would be nice to think that without those compliance requirements, that as designers, we're all passionate about better buildings, and we were doing this anyway, so to speak, because there's a lot of beauty, I think, in the architecture that evolves something that is carbon friendly and biophilic. I hope I've answered that question. Yeah.
That's great, John. I mean, I guess, and that's a really compelling argument in terms of, I guess, companies and shareholder value. What about governments and institutions? Will those legal changes also apply to them?
Yeah. Well, they're leading with the changes. Like a lot of, if you can't get work, you can't do a $200 million job at university these days without having a very clear pathway and approach to adaptive reuse, to where your carbon sort of footprint is, and the biggest issue that universities are having in terms of achieving their certifications for decarbonisation is embodied carbon. They're getting operational carbon down to low figures because of solar and wind, but the next step now is to get their embodied carbon down through the way that existing materials are used on sites, and the way that consultants can work with that and bring the right new build to augment that without blowing their carbon budget. So it's real, it's happening. It's also fair to say that probably infrastructure in government needs to catch up. So I'm talking about roads, rail, and stuff like that, where lots of concrete and lots of earth is moved, and there hasn't necessarily been, dare I say it, a life cycle analysis that looks at that carbon footprint hasn't necessarily been the driver for a lot of those projects. But from my understanding, in talking to leaders in industry and government, they're aware of what's happening, and they're aware of the obligations, and they're looking to consultants, people like us, for solutions. So it's definitely, it's not about to change, it's changing, and it's going to change quicker the closer we get to 2030.
That's great. Thank you, John. That's a great call to action for everybody, I think. Yep. So thanks again to John, and also to Elisa for managing the slides. Excuse me. Thank you so much, everybody, for joining. And just a reminder that these lean-ins are recorded to view later, and you can get notifications of these by subscribing to the AIA's YouTube channel, YouTube @ Oz Architects. Thank you again, and everybody have a fantastic day.